Hi, and welcome to a lesson on programming output ports. Before viewing this, you should have read Chapter 2 in your textbook, up to but not including data types in C. You should have also watched the Intro to Embedded Control video and the Output Ports and Relays video. Okay, as we said last time, I/O ports are what allow us to connect the devices to the microcontroller in order to bring information in or control something on the outside. And we said before that the PIC microcontroller includes 5 general-purpose I/O ports, labeled port A through port E, and most ports have multiple purposes, and as we'll see later in the course, a microcontroller has a lot of features, but you can't use all the features at the same time, so they have to be programmed for a certain thing. So, because a port can be either input or output, but not both at the same time, we have to define whether or not it's going to be input or output. So each port, up here you're looking at port A. We have a port that has 8 bits, labeled bit 0 through bit 7. Remember, we always start counting with 0 in computers. And we have another register. A register is just like a memory location inside the chip. So a port is a register that actually has wires that connect to the outside world, and each port has a corresponding register that's labeled tris and then the port name. Tris, I'll talk about what that means in a minute, but let's call this the data direction register. And what that does is it defines whether each bit of port A is going to be an input bit or an output bit. And remember that we said that ports are bit addressable, so that means that some bits can be inputs and some bits can be outputs. And the way that this tris register works, I'll explain what tris is. Tris stands for tri-state, and in digital circuits we always think of an output as having 2 possible values, 1 or 0, but there's actually a third value, and that's the tri-state condition, or the high impedance. That's where it's electrically disconnected, so it doesn't do a 1 or a 0. Okay, I think they should have called this the data direction register, but they didn't ask me for advice when they named this. So anyways, the tris register defines input-output for port A. Tris A defines it for port A. So if we were talking about port B, there'd be a register here called tris B. Okay, you understand that? So what I do is, if I want to define ports as inputs or outputs, what I have to do is first define these bits in the tris register. And if I want a bit in port A to be an input bit, then I program that corresponding bit in the tris register with a 1. So I'm going to write a 1 here, and a 1 makes this bit an input. A 0 makes a bit an output. Okay, so everywhere I've got a 1 in a tris register, the corresponding pin on that port is an input. Everywhere I've got a 0, the corresponding pin is an output. And I always remember that a 1 looks kind of like the letter I for input, and a 0 looks kind of like the letter O for output. Okay, now each bit in port A has a name, that's port A, but we also have individual bits. Remember that the ports are bit addressable, so each bit has its own unique name, and we're going to call bit 7 of port A RA7. The R stands for register. Okay, so that's RA7, RA6, all the way down to RA0. So each one has its own unique name that is identified within the microcontroller. Okay, a microcontroller is very versatile because it can be programmed to perform different tasks. And a program is just a set of instructions that tells the microcontroller what to do. So we think of the physical circuitry of a microcontroller as the hardware. The programs are known as the software. If a microcontroller were a chef, then the pots and pans and stove and utensils would be his hardware, and the recipe would be the software. The same hardware can cook up a lot of different dishes just using different recipes. Okay, so there's your hardware, there's your software, whoops, there's your software. Okay, when it comes down to it, every computer operates in machine language. Okay, machine language is just binary 1s and 0s. Okay, every computer is just digital circuits, and those 1s and 0s are what control the circuits. Okay, that's the only native language of a computer, and every computer program that's running is just executing these little 1s and 0s all over the place. Okay, now don't quit the class yet, because we're not going to program in binary. Okay, be glad you weren't an electrical engineering student in the 1940s, because that's what they had to do. But machine language is very cumbersome. We like to write our programs in higher level languages that are a little bit more like English. But before these programs can run on a computer, they have to be translated. And the good thing is that we can write a computer program, or we can buy a computer program called a compiler that translates the high level language, or the English-like language, into machine language. So we'll talk more about that later, but you should have already read about compilers in the textbook. Okay, here's a little chunk of one computer language called C. C is a very popular programming language for microcontrollers. It's very similar to other languages like C++ and Java, which are used to program personal computers, web pages, and things like that. Okay, so C is a very good language widely used in microcontrollers. So let's take a look at a fairly simple C program. Now I admit this doesn't look all that simple. Nothing is simple, okay? Think about it this way. If it were simple, anyone could do it. And if anyone could do it, you'd make minimum wage doing it. That's not cool. So we got to deal with a little bit of complexity. But it's not that hard to think about a little chunk at a time. So we'll take a look at it a little bit at a time. Okay, let's start with the top. That first line, the pound sign or the number sign, followed by the word include, that tells the C compiler that I want to include another file in this program. So there's a file called pic.h somewhere that somebody else wrote. That's cool. No, we didn't have to write that. And what it does is it has a whole bunch of names of registers and ports and things like that. And all we need to know about this line is you're going to include that as the first line of every program you write in this class. Okay. Over here we have a set of lines that are basically, they're just comments. They don't mean anything to the compiler. They don't get translated into machine language or anything like that, but they tell something to the programmer. Okay, we'll talk more about comments in class, but at a minimum you need some comments to tell you know, what the program does, who wrote it, when it was last updated, so that, you know, programs need to be maintained and people need to know who's in charge of it. Okay, a comment begins with the slash asterisk and it ends with an asterisk slash. So everything in between here is ignored by the compiler and not translated. Okay, this line right here, the PIC microcontroller has a lot of different features, and this is turning certain ones on and off, and we really don't have to worry about that because you're going to include this line in every single program that you write. Okay. These two slashes here identify a comment as well, just like they do up here. When you see two slashes in a row, everything that follows it is a comment to the end of the line. Okay? This pair of symbols is used to write a multi-line comment. This one is just, you know, you want to write, the rest of this line is ignored. Okay? Your actual program starts here, right after this comment. Now, don't worry about what this means. All you need to know for now is that every program is going to have this void main with the word void in parentheses and an opening curly brace and a closing curly brace. Okay? When you write a program, just type that in immediately and then you can stick the cursor here and you start typing in your program. So every program has this. We'll talk later about what that is, but every program has a function or a set of functions, and in this case we have at least one function called main. Okay? Don't worry about the voids. We'll talk about that later in the course. Okay, now we get to our first actual command. This is the first thing that actually generates machine language and writes and does something to the microcontroller. Okay, this says take the tris register, and this thing right here is not an equal sign. Okay, we're going to rename that. That's called the assignment operator. And what an assignment statement does is it says take what's on the right and copy it or assign it to the variable or the register on the left. So it's going to take this number and put it in here. Okay. Numbers in the microcontroller in the C compiler is going to assume that all numbers are in decimal unless you tell it otherwise. Okay, so this 0b says this is a binary number. Okay, since we're dealing with binary, we're dealing with individual bits, it's helpful to just write this out in binary. You kind of have to write it out in binary anyways. Why bother converting it? You might as well just type it in and let the system figure it out. Okay. So this says take this number, this binary number, all ones, and the last one is a 0. So bit 0 is going to be a 0, the other ones are going to be a 1, and move it to the tris register, the tris A register. Okay, and this says send a 0 to bit 0 of port A, and we already know that bit 0 of port A has a name, and that's RA0. Okay, so there you go. It's not that intimidating when you look at it a piece at a time. But remember that all programs are structured just like this. They all have this include statement at the top. Okay, they all have this config line. They all have a block of comments here. They all have the same exact config line followed by a semicolon there. Okay, they all have void main with the opening and closing brace, and they all have some instructions in the middle. Okay, we can also, RA0 is not a very descriptive name. Okay, it's descriptive as far as the computer is concerned, but I don't know what's connected to RA0, and in a fairly complicated system, you've got a whole bunch of devices connected to different ports. You don't want to have to remember what those are. So we have a way of defining custom names. Okay, and we can do that using the define directive. And what the define directive does is it says, you already know this name, I'm going to call it by this name, and anywhere I use this word, you pretend I said this. Okay, it just does a direct translation. So if I say #define furnace control relay, now in your names you can't have any spaces, so we're going to cram it all together and call it furnace control relay is the same as RA0. Okay, I'll get to that one in a minute, but define furnace control relay as being the same as RA0. So right here, when it sees, instead of saying RA0 is assigned the value 0, I'm going to say furnace control relay is assigned the value on. Now, what's on mean? Well, I'm defining on as being 0. So this line right here does exactly what this line used to do, okay, but it's a lot more meaningful. If I see a line that says RA0 is assigned 0, that doesn't really tell me very much. If I see furnace control relay equals on, that tells me, hey, I'm turning the furnace on. Okay, and the cool thing is, when I do that, I don't even need to write a comment on that line. This line is self-explanatory. Okay, and the structure of the define directive is #define, that says I'm defining a name. This is the name that I create, and this is the name that the compiler already knows. Notice there's no equal signs in here, there's no semicolon at the end. This is the exact structure for the define directive. Okay, so there it is, C programming in a nutshell. You're ready to do your online questions and your lab prep activity, and then we'll move on to the next topic. See you later.